Hi, it's Victor again. Welcome back to the Victor's Learning Hub channel. Hope you're having a fantastic day. And today we're going to be focusing on some calculus. So what we are focusing on today is Unit 2 of Math Methods, and specifically we are we are going to be going into topic 3, and we're going to be focusing on the introduction to differential calculus. So basically, your first stepping stone into calculus, which you'll build upon for your whole senior high school or studying math methods. So it's going to be a really good start to your calculus journey throughout school. So yeah, hope you enjoy this. So let's just get straight into it. So this is from the Jacaranda Year 11 Math Methods textbook, and the syllabus link we're focusing on today is so using, which is our cognitive verb here, the rule of f of x equals the limit as h approaches 0, where f of x plus h minus f of x divided by h. So we're going to be using this rule here. It may not make much sense at first, but we'll dive deeper into that later. And another cognitive verb is to determine. So determine the derivative of simple power functions and polynomial functions from first principles. So let's consider this definition first and explore this definition before we get into what this rule actually is. So we're talking about the instantaneous rate of change of f at a particular point. It's represented by the slope of the tangent line to the graph of f at this point. So a graph, which can be represented through a function. Okay, let's consider this in more detail. So when we're talking about an instantaneous rate of change, it's only being referred to at one point. And what we have is a tangent line. And what a tangent line is basically a line that only touches the point once. So it's something like this. All right, you've got a point and it's only touching it once. So that is what we call a tangent line. And we can do this really for any graph. So let's just say we have a quadratic, for example, all right? And we want to draw a tangent line onto the quadratic anywhere. So let's say I want to use this point here in green, okay? And it'd be good to grab a ruler. So grab a ruler, try and draw it carefully along the ruler. This would be our tangent line because the tangent line only touches the function once at only one point. It's not a secant line, it's a tangent line. Okay, and that's what it's referring to as a graph here. So, for example, we've used a quadratic here. So let's consider in more detail in terms of how we get to our formula. Let's just say this graph here and this function is called f of x. So if we want to find the instantaneous rate of change on this graph, so what should we do? How do we actually do that? So let's just call this point x right here. Why not? Let's just x, okay? So we've got x right here, all right? Here's my first point, and then here, the y value here must be f of x. Let's just call this point h here. So I've got my point h here. I've got a second point here. The y value at the point h must be actually f of x plus h, because you're adding h. You're going this way. So this length here would be x plus h. And this length here would be f of x plus h plus f of x. So when we're talking about instantaneous rate of change, we want to only refer to one particular point. So what we want to do here with actually these 2 points is we want to get them to as close as possible to each other, all right, until a point where they will just meet. So if we want to do that, we're trying to find a gradient, slope at this point. And we can measure the slope, going to be the delta y over delta x, the difference in y over difference in x, okay? We can actually see here, this is actually our difference in x, and this here is actually a difference in y. Basically, this is our rise, and this is our run. We usually denote it by f of dash x, so making sure you include this dash here, or you may see it as the dy over dx, which is the difference in y over the difference in x. So we're going to be using this notation here, this symbol here, as f of dash x, the gradient function of x. If we're going to refer to our delta y first, our rise, f of x plus h minus f of x. Cool. Okay, awesome. Now I want to get my run, my delta x. My delta x actually is going to be this distance right here, x plus h. So it's going to be x plus h, but we're not done yet because we want to subtract based on how far this x plus h is. It can be however far it wants to be. And we want to subtract that from x, because x is basically a baseline point. The length of h we actually add to x. We can do it however we want. We don't know what it is. So it's going to just be subtracted by x, which is a fixated point. These x's just cancel out, so that's just going to be h. So in the end, on the denominator, it's going to be h. Okay, cool. So we've got this, but we are missing one thing, and that's our limit actually. So technically, if you're going to write this in the exam, you'll probably lose maybe like half a mark. It's going to be taken away from you, because what you need to include is the limit. And our limit is when h approaches 0. So referring back to the arrows I've drawn here, the distance of h as I've drawn here, what is trying to say with the limit? The limit is that it's when these 2 points keep coming together, keep approaching together until this distance between h is 0. Now we know that h is like a length away. So h has to be greater than or equal to 0. It can't be less than or equal to 0. It cannot be a negative number. A limit basically is our maximum capacity in a way, if you want to think about it in that way. You cannot go over it. You can't keep going from h. You need to stop at 0. So that's why we call it a limit. So really the right answer here would be f of x is going to be f of x plus h minus f of x over h. And don't forget your limit, as the limit when h approaches 0. So with this arrow here, always saying is approaches. So that's how you describe what this arrow is meaning. As these 2 points get closer and closer together, the distance here with h, it's going to become much, much less. So hopefully that makes sense. If that doesn't make sense, you can just pause the video and think about it for a little longer. It can take some time to understand, but that's the general gist and the basics of it. And I forgot to put my dash here. Make sure you remember to put your dash. You're gonna lose a mark for that as well. It is perfectly fine as well if you put dy over dx as well. They mean the exact same thing. Either way, make sure. Anyway, the general gist and using this principle, this rule, is referring to the slope, basically our rise over run, and our limit is basically how close the 2 points can actually get together until h approaches 0. So now let's try this question out. So if g of x equals x squared minus 6x, calculate the gradient function using first principles. So remember, we need to be using first principles. You'll learn throughout doing more calculus, there are other ways, such as the power rule, the quotient rule, the product rule. But you need to make sure you read the question properly and do it the specific way it's asking you. So remember, we need to use first principles, which is what we've learned. And we are we're actually calculating the gradient function. That's what our cognitive verb is asking us, the gradient function, which is basically our instantaneous rate of change at a given point on the function. Okay? So g of x equals x squared minus 6. Okay, that's what we're focusing on. To make it a little bit easier, I'm just going to call this f of x. It doesn't really matter what you call it, just because we've focused on using the variable f of x throughout this video. Of x equals x squared minus 6x. Also, just a heads up, you will have this in your QCAA formula book, so you will not have to remember this, thankfully. You can just pull it out, but it's still good to get a general understanding and try and remember it if you do enough practice to remember it. Okay, so f of x equals x squared minus 6x. I want to focus on this bit first. F of x plus h minus f of x. The reason why I want to focus on this bit first, because it's going to take up a lot of space. So I'd recommend you put this down somewhere else in your working. Okay, so let's calculate. So if we know that f of x equals x squared minus 6x, all we are doing is adding h as specified here to the first bit. So if we have x squared here, this is our first term which retains a variable of x. It's just going to be x plus h squared. We still retain that squared here. We've just added that h. Next, we need to do minus. So minus 6, we still have this x here, so we still need to add h to it. X plus h. Now we want to focus on subtracting f of x, which is pretty simple. So we just do a subtract, and then we can just do in brackets x squared minus 6x. Cool, now let's just simplify. So we know it's going to be x squared plus 2xh plus h squared minus 6x minus 6h minus x squared plus 6x. Okay, great. Let's cancel out the terms. So we can cancel out this x squared here. We can cancel out this 6x here. What we are left with is 2xh plus h squared minus 6h. Okay, great. So we've gone to this bit here. Now, one last thing it's really important to do is to actually take out the common factor. So we know we have a common factor of h in this scenario because we've canceled out those these x terms here that do not have a h. So we can actually factorize h out. So we can just go h multiplied by 2x plus h, because we still have a h squared here, minus 6. So this is the final thing. You should end up with something like that. So let's go back to our original formula. So f dash x equals, so with f of x plus h minus f of x, which we've gone down here. So what we can do is just sub it in. Make sure you apply your limit before. If you do not apply your limit, you will lose marks on the exam. Okay, h 2x plus h minus 6 over h, because we still have that h from the actual formula itself. Now, the nice thing of what we've done by factorizing out the h is that we can actually cancel these h's out now. So that is the main reason why we factorized. Now, the limit of when h approaches 0 is going to be 2x plus h minus 6. Okay, great. So now I've got 2x plus h minus 6. And reiterating why it was so important to actually cancel out the h here is because we actually want to get rid of this limit really here, because we can, it's actually mostly appropriate now to actually let h equal 0 in a way, that these points can actually get together so close that h will equal 0. We know that anything divided by 0, that is just not going to work. We can't divide things by 0, but since we've canceled the h on the denominator, we can now do that. So f dash x is going to be 2x plus 0 minus 6. Therefore, f dash x is going to be 2x minus 6. Okay, awesome. So that should be part A done. So now we need to find the value or values of x where the gradient equals 0. So the gradient equals 0, and we need to find the values of x. What we're trying to find here really is when f dash of x actually equals 0. So we can let f dash of x equals 0. We can sub that into our formula. 0 equals 2x minus 6. 6 equals 2x. Therefore, x equals 3. Okay? Pretty self-explanatory after that. So we know that the value of x will be 3. Now, a good strategy I'd recommend to do is to further check your answer by using your graphics calculator. So let me get my graphics calculator up here, okay? And let's go to run matrix, okay? Press options, press F4 for calc, because that's calculus, and press this D of dx here. So now I think a good thing, especially when you're going through exam, to double check your answer is to actually use your graphics calculator. So I'm going to demonstrate using the Casio Graphics Calculator here. So what you want to do is go to run matrix, want to press options, F4 for calc, for calculus, press this D of dx, okay? And just go back to your original equation. So our original equation was x squared minus 6x. So let's input x squared minus 6x. And we know that we've got x equals 3 here. So that means that when I put x equals 3 here, and the answer should come up as 0. So at x equals 3, the instantaneous rate of change of this quadratic here should be 0. And voila, it gives us 0. So that does prove our answer is reasonable. You can make another statement if you want, saying that therefore the graphics calculator does say when x equals 3, the gradient function is going to be equal to 0. So okay, so now I'm going to show you one last thing. It's actually going to show this as a visual representation of Desmos, just to further consolidate your understanding. So let's have a look. So now I'm just going to take a little bit of a step further and actually find the equation of this tangent line at this point, the instantaneous rate of change at this point. So we know that the gradient is going to be 0, okay? So when we're talking about a gradient equaling 0, we call it a zero gradient basically, because there is actually no really that rise over run in a way. It's just a complete straight line. There isn't really a slope in a way. It isn't tilting positive or negative, whatever. It's just completely horizontal. We're focusing on x equals 3 here. So let's just sub in x equals 3 into our formula. F of 3 equals 3 squared minus 6 times 3, which is 9 minus 18. Therefore, f of 3 is going to be negative 9. So my point x, y is going to be 3, negative 9. All right, awesome. So now we can just sub this into actually a point slope form, which is y minus y1 equals m of x minus x1. So we know that our slope here is going to be 0, and we've got our x and y values, which we can refer to up here. So y minus negative 9 equals 0 of x minus 3. Okay, so that's going to be y plus 9 equals 0. Therefore, y is going to be equal to negative 9. Y is going to be equal to negative 9. So let me show you a visual demonstration of this right now. So the cool thing about Desmos actually is that I actually can find the instantaneous rate of change for you simply by doing F and pressing dash on your keyboard and doing F dash of X. So let's just double check our gradient functions equation by typing into Desmos to see if it matches what it's been given by here by F dash of X by the red linear line. So we know it should be 2x minus 6. Awesome. As you can see here, it perfectly overlaps. So we know that what we've got is right. So we've basically just used technology to evaluate the reasonableness of a solution. So let's see if our equation of the tangent line that we've got at point 3, negative 9 of y equals negative 9 is actually correct. So let's put in our point first, 3, negative 9. Awesome. If you can see it right down here, I'll label it as well, 3, negative 9. So let's now put in our equation of the tangent line, which is y equals negative 9. So as we can see, it is a tangent line because it only touches this quadratic once at that point. And in fact, this is the turning point of the quadratic. That's why the gradient function, the slope of the function is 0 at this point. If we even remove this point, we can see that Desmos has created an intersection point for us right here of 3, negative 9. So we know that is going to be right. Okay, so to quickly revise what we've just learned, let's just go through this question quickly. So identify which of the following denote the gradient at any point on a graph. One or more answers may be correct. Okay, so I'll give you 5 seconds to think about it. If you need more time, just pause the video. 5, 4, 3, 2, 1. Okay, let's go through it. So f dash x, we've literally gone through this the whole video, so that is right. The limit of h approaching 0 of f of x plus h minus f of x over h, that's what we've used. This one is wrong because they've applied the limit wrong here. The limit of h does not approach infinity, h only approaches 0. This one is right as well, they just haven't simplified the denominator. X plus h in brackets minus x, that is the same thing as h itself. This really should be h and n, but technically this is right. It isn't the most simplified form though. This one is wrong because they are missing the limit. They haven't applied the limit at all, so they should be applying the limit of h approaching 0. Okay, so let's just quickly refer back to what we've done today according to the syllabus. So we have successfully used the rule of f of dash x equals the limit of h approaching 0, where f of x plus h minus f of x is divided by h. We've done this to determine the derivative of simple power functions and polynomial functions from first principles. All right, thanks for watching.